Hi, my name is Mr. Evangelista, and welcome to this episode of Evangelista Science. The first thing we're going to talk about is the difference between an electrophile and a nucleophile. So electrophiles are positive, and they are usually attacked by nucleophiles. Now, nucleophiles have a negative charge, and they have a lone pair of electrons. And so these lone pairs of electrons, which are negative, are actually going to be looking for these positive ions to react with. So electrophiles are positive, nucleophiles are negative and have an electron pair that can be used to form some reactions. We're also going to talk about homolytic and heterolytic fission. So homolytic is when you split a bond and the electrons are shared evenly between the two species. Notice this makes what we call free radicals. Radicals are uncharged. They contain at least one unpaired electron. And again, this results from homolytic fission. So when we split the energy of that bond, the electrons go to each species equally. We have heterolytic fission, where when we break that covalent bond, both electrons are going to one atom. And so what this does is it creates one positive and one negatively charged atom, since both the electrons are going to one species. Now, just some conventions. You always have to draw, when we draw these mechanisms, you always have to draw arrows from either bonds or electron pairs, because that's where the reaction is starting from either bonds or from electron pairs. If you're showing a movement of an electron pair, you can use this double-pronged arrow. However, if you're showing the movement of just a single electron, like in homolytic fission, you have to draw these single-pronged arrows. So organic chemistry, this is where the fun begins. Now, these problems I show you are really difficult. They are college-based problems. We're not going to be doing any of these, but it's just an example to show you kind of what is the purpose of learning all of the reactions that you're about to learn. And so in organic chemistry, what happens is they give you a reactant, they give you a product, and they say, what do you need to add to change this reactant to this product? And that's what we're going to be going over. We're going to be going over a bunch of tools and different reactions that you can do to kind of manipulate these organic compounds. So first we're going to talk about alkanes. You'll notice that alkanes only have single bonds, and they are pretty much just carbon and hydrogen. There are three reactions that you need to learn for alkanes. They are combustion, incomplete combustion, and substitution. So let's talk about the first one, combustion. We've seen this before. You add oxygen and some heat to a hydrocarbon, and you get carbon dioxide and water. Don't forget the heat. You can also have incomplete combustion when there's not enough oxygen. It's the same reaction, except for instead of carbon dioxide, we actually create carbon monoxide instead. And you also need heat for this one as well. So both of these need heat as a catalyst. Now, substitution. Substitution, what it does is it will add some type of halogen to your alkane group. So if you have CH4 and you wanted to add a chlorine to it, you would use substitution. Okay? Remember, this is working with alkanes, and the catalyst that you need to do this is UV light. UV light allows this to happen. So let's take a look at a little bit more detail on how this works. So we have three steps on substitution reactions. The first step is initiation. What's going to happen is we're going to shoot UV light at these chlorine molecules, and it's going to use homolytic fission to split the energy in that bond to put one electron with each chlorine, and so we have two chlorine radicals. Those radicals are very unstable, and they're going to react with anything they come in contact with. And that is the propagation step, the second step. Notice each of these steps both use and produce a free radical. So the chlorine maybe will go and attack the CH4 to make CH3 radical plus HCl. And maybe that CH3 radical would go and attack the chlorine to make CH3Cl and reproducing the chlorine radical. Maybe that chlorine radical is, we can't control these reactions in the test tube. They're going to react with whatever is in the test tube. So it could be that chlorine radical goes back and reacts with that CH3Cl to make CH2Cl CH2Cl radical. Maybe that CH2Cl radical will go and attack a chlorine and we'll get CH2Cl2. And this can go on and on and on, and we can actually get all of the hydrogens off of the chlorine, off of that carbon, and replace them all with chlorine molecules. We won't only get CH3Cl, we'll also get CH2Cl2, we'll also get CHCl3, and we'll also get CCl4. And so that's the thing with these organic reactions. They're very, we can't really control what they're going to react with. And so that is where extraction techniques are very good in the lab, because each of these have different chemical properties. So you need to know how to extract. What if you just wanted to extract just the CH3Cl? Well, that will have different extraction techniques than the CCl4 if you wanted to just extract this one. The last step, the termination step, is going to remove the free radicals from the mixture by reacting two radicals together. And so we could get, in the end, chlorine gas, which is what we had in the beginning, or we could get the CH3Cl combining, which is what we want, or we could be having the methane molecules, the methane radicals combining together to make ethane. So as you can see, we have a whole wide variety of things that we actually get from this reaction, but maybe the only thing that we wanted was CH3Cl. In summary, alkanes go through three types of reactions. We have combustion, which uses heat to make carbon dioxide and water. We have incomplete combustion, which uses heat and oxygen to make carbon monoxide and water. And we have substitution. Now, substitution, you do need to know these three steps, and you do need to be able to kind of draw out the mechanism on how this happened. Okay. One quick thing on colors that you need to know. You need to know the colors of the halogens. So especially bromine. Bromine is orange and brown. So we see from this picture here, if we have bromine in water and we shoot UV light at it, it becomes colorless as that reaction that we just went over occurs. In dark, without the UV light, without the catalyst, we don't have any reaction that occurs.